Okay, welcome to this webinar where I'll try to describe a little bit the perception or the feeling that really it is very, very, very important to be able to sweep across many different levels of detail in the performance analysis of parallel applications. I'll be giving a start with a few kind of analogies and examples and explanation of what I understand by these levels of details. But I will elaborate on those based on examples towards the end. So let me start by switching to the what do we do when we analyze physical systems? We really face with physical systems really very large problem spaces. Okay, so we can both in the spatial dimension, in the time dimension, we analyze systems which can be very large, and part of the objective is really to be able to analyze the very large values, the very large scales. But in reality, microscopic structure is a very important component that determines the macroscopic behavior. So really, it's really needed to go down and drill down and really understand also the innermost levels. This is the kind of message, the kind of situation where the message I want to convey is the scalability is not about size. It is certainly about size, but not only about size. And probably from my point of view, it's more about dynamic range than absolute size in itself. It's about the ability to seamlessly sweep across these different levels or dimensions or the granularity in those dimensions. And in the performance analysis world, these dimensions are essentially resources. Let's say this, what I would call the spatial dimension, where we have examples here of very rough, very approximate, but just to show that really the number of resources that we may want to look at or analyze may be large, not even considering apart from the computation resources, other computations like memories, interconnects, or translation units. So really the spatial dimension is large. The time dimension can be very large, can be huge, from a large run of seconds, minutes, hours, to really those things the behavior of those things depending also actually on the microscopic sub-nanosecond type of behavior of them at the microarchitectural level. So how do we analyze this very, very large space? This is about the problem space. The other thing is an analogy is about how or other systems where we are used to navigate on something which is only a few orders of magnitude in difference in scales, but we use these geographical systems that let us zoom in and zoom out and maybe observe the thing at the very coarse level and then dig down into very details. And I think this is kind of the objective that we should deal with our tools. In these systems, you can navigate seamlessly across those scales. You really don't realize actually when you are changing to an innermost level of representation or data storage that contains the lower level of description. Well, maybe sometimes one realizes those transitions, and maybe if you're driving in a foreign country and you have no enabled your roaming, you may feel that. But in reality, on real practice, it's pretty seamless, this navigation. So this is the analogy and the kind of features where I would like to see in terms of performance tools behaving. Just a small thing. I did ask a little bit, just these times you have to ask ChatGPT about what he thinks and about the analogy, and it's, well, somewhat similar, okay? Probably, I hope I can say a little bit more of detail on the internals at this level during the presentation today. But this is the basic idea. And what I think is important is to be able to really navigate this space of performance data, zooming in, zooming out. Probably it's when zooming out, aggregating information, when zooming in, really showing the detail, but having a very wide range, a dynamic range of scales that can be visualized out of a single run of the performance data of capture for a single run. And I just wanted to say it's not only about the physical dimensions that one looks at, but it's also about the semantics on what is the information that one displays for each of those points in space-time dimension. It's about the metrics, the flexibility in those metrics, and how those things convey to the analyst information about the behavior of the system. And the message I would like to give is a message I think is both for tool developers, where I think it's important that they do try to have this mindset and try to support this seamlessly sweep across scales to enable it happening in a very productive way. So try, for example, minimizing clicks that you have to give to show the information at the different levels, or to zoom into it, or to display it. And also, I think it's a message for analysts. Very often, I think we tend to be probably a little bit too static to setting our focus on a given level and not digging down very much. And I would like to encourage people to really look for deep insight, go deep down into what is the reason of the behavior of the systems, because this is what will help us. It will allow us to improve them at the end after that. Okay. So this is about the message I want to give. I will start by a very high level view. What is the typical practice, in a sense? What we look from, maybe from 10 kilometers, maybe much farther away, and how we do this in performance analysis. And we essentially look at elapsed time. And we just report, maybe for different core counts, for different resources, we report times, speed ups, or efficiencies, but it's a single number for one execution. My point is kind of analogy, or how to describe the Earth from outer space, okay? And maybe you can do it with one word, 2 words. You can say blue planet and you're done. But really, with this, you are missing a lot of, yes, there's a lot of sea, there's a lot of ocean, but there are deserts, there's jungles, there is rivers, mountains, snow. So this kind of single number, which of course is very important, the elapsed time is the important thing at the end, but in terms of giving understanding, reasoning on just these plots, I think is probably not enough insightful. But certainly, looking at things from very, very, very high is really very important. What are we trying to do in terms of that in POP? We probably, even if looking at things from very far away, instead of describing them with one model, with one number, we try to describe them with maybe 6 numbers, as we have here, a model with 6 components, which are more fundamentals, describe more fundamentals of parallel programming than what just time does. So this is a model where we describe how much the difference of work assigned to the different resources, or how much real order, real dependencies between things impacts overall performance, or how much the actual non-instantaneous nature of the transactions that are required to communicate or to control different resources take. This lets us do things like tables where we display, as we scale the number of cores, we can display the efficiencies, in this case percentages, and we can reason about how they evolve with the scale. We can reason about how do they relate or compose. You may have a value which you may say, okay, it's fine, it's okay, reasonable, but it's actually composed of something which maybe starts being a little bit worse, combined with something which is quite good. So these kind of relationships, you can still reason about them. We typically do this in a post-mortem kind of, so we actually get the data for all these different runs. What I'm trying to say is that these metrics, we believe, are also very valid for doing, to minimize the amount of experimentation or real data capturing that you really need to do, and storage, by doing these things online and determining the model in terms of the model, and really decide based on that which really points you will be sampled, which sample points you will be really gathering full data. But in reality, what I'm going to look at today is actually a few examples, all of them just post-mortem, try to see how we post-mortem can squeeze most of the data captured in trace by system. I'll be using the BSC tool framework and capture the information in the trace, see how we can drill down, how navigate on it. And I will be doing that on examples on CPU only, standard general purpose processor things with GPUs, be it numerical simulations or AI training, or even I will be talking a little bit about the RISC-V vector co-design examples. Some of these examples come from POP. Some of those are from other collaborations that we have or we are having. And I will start by a large-scale CPU-only example. And in this case, we have actually stressed one application, which was actually analyzed in one of the POP assessments. We have stressed it to do a kind of what happens at very large scale. And we have run it on 112,000 threads. And when you do that, even in this case, even you get a trace, even just for one single algorithmic step of the computation, you get a fairly large or sufficiently large trace that certainly the tool cannot handle. The question is, can we structure this information in levels, in hierarchies, that each of them give us a top-level view and then dig down into innermost level views? And how seamless is that done by the framework? And how could that be done more seamless with future developments? In this case, this 134 gigabyte result in only 1 gigabyte if you just filter and you just select collective MPI calls and computations that take more than 5 milliseconds, useful user level computations that take for more than 5 milliseconds. We can see it. We can see the structure of these 14,000 processes, and we can see that it has phases where it is intensive barriers. There are other phases where you have intensive use of MPI or reduce in terms of collectives. Actually, this view for the whole run lets you see that those two phases may be different, and you may want to analyze them separately, but you may want to look at them. If we are at the, let's say, at the 10-kilometer high view with this, we can even go farther away. And can we, for each of these regions, come up with the metrics that I was mentioning? And these metrics summarize the internal behavior here, and they would tell you, well, you may see a lot of all reduces. Don't worry, communication is not a problem from this point of view. It is a load balancing problem. So this thing that the going high can give you the perspective to be able to see the global behavior and what is important globally. Of course, even on the same data, which is 1 gigabyte, we can even look at it with the 100,000 threads and display the 100,000 threads for this, in this case, 25 seconds execution. And we display here how long are the individual computations in the range of from 0 to 50 milliseconds. The darker the color, the longer the computation that takes place in that region. And you really see, again, a lot of insight, a lot of information, at least, that may draw your curiosity. You can certainly apply, so go back to the looking from outer space and looking at the very global general metrics, but you can use the example, the view to say, maybe I'm interested in looking more at this thing, this region, or maybe I'm interested in looking more at why they start skewed with respect to each other. Or maybe I want to look at this thing which has iterative structure, but I want to understand a little bit more. I've actually gone into this last case, and this is the next level. So what we did is we get now a trace which is out of the original 130 gigabytes. It's a trace which describes only one iteration of this innermost step, but that has all trace events, all MPI information, all OpenMP information, so has all the events. And this is 1.7 gigabytes. In the outer view, we have seen that the behavior is iterative, so this is a good representative of that whole iterative region, and we can look at all the MPI calls, and we can see a little bit of a skew here. This is what you would associate with semantically a little bit kind of serialization, dependencies, order of the computations. Probably you would blame MPI or reduce as taking a huge amount of time. Is it sufficient to go and blame the MPI implementer saying your MPI or reduce has to be better? Well, certainly not. Again, if we go to a higher level of point of view, we can see that yes, communication does have some impact, but really the thing is mostly load balance dominated, the efficiency, and the model is multiplicative, so a low value actually implies really big loss of efficiency. This was looking at the level of processes, maybe at the little bit lower level, at the level of threads. What we see, we actually, the same part of space, time, we really see a little bit of a skew in the duration of the computations. Here, the color represents how long are the computations. And we see a little bit of a skew, but we don't really see at this level, or doesn't seem to be one process taking much more than the others, which is what load balance defines. And probably it's an effect of a scale. Maybe we want to zoom into a few threads. And here we have a zoom into a few thousand threads out of the 100,000s that we had. And we really see this behavior where, and also at this level of processes where the MPI calls kind of elongate here. There is kind of a projection of computation towards in time for happening only for some process separated actually by a few hundred, so a few hundred of ranks. So it's kind of indicative of some behavior which may be drilling down even a little bit more might help us identify what happens and if that is normal or reasonable, that's what we would have expected or not, and what are possible causes for fixing it or correcting it. In this case, this is a zoom in just 64 threads of that. This was an MPI plus OpenMP application. Each of the processes taking 8 threads. And we actually see some processes, all the threads work for the same amount of time. Some processes, there's only a few of the threads that work. So this introduces the load imbalance. Actually, you see it, and this is what continues here. It's not always the same pair of threads that does the work. So you really gain insight about the internal behavior. This kind of insight at microscopic scale is something that in this case, in this assessment, for example, the people has been discussing with the code owner. It has been identified. It may be a simulation code that may be a few 100,000 lines of code, but fixing this is fixing 20 lines of code has been fixed. And this is one of the features that can really be improved. My objective is not really to look at the specific analysis or the specific applications, but to convey the feeling, I hope I try to convey the feeling that drilling down is really a very important thing. And this was the first example, and I'm going to switch now to the second example, which is about an MPI plus CUDA application. Not very large scale. I'm talking about something like 32 GPUs, very relatively small, one can say. What I want to focus is on actually a tool that we have been developing in the last year, 2 years, which is nothing more than just a translator from NVIDIA, tracing formats, tracing information to Paraver. The idea is to leverage the Insight Systems acquisition system and claiming that Paraver would have superior browsing capabilities in terms of this dynamic range of digging in and zooming out. This kind of transformation can certainly be done with any other kind of tool developer which acquires information. And what I want to try and show is how can we look at the data for these 32 GPUs in this Paraver views. If you look at very zoom level, well, it's slightly different. Maybe there's different color, but the kind of things that you see is very much the same. And as I said, the raw data is the raw data coming from Insight Systems. In this example, was an MPI plus OpenMP application. The trace was 33 gigabytes. So less than before, but still not in something that Paraver can really load and manipulate. We have to go to this kind of multi-level approach. And the first level, what we do is just generate trace which has out of the original one that has only MPI calls. This trace is 3 orders of magnitude less than the original, but this trace can be visualized, of course, only the information related to the MPI calls, and we can really see structure in it, and we can really see do timings of the duration of iterations. All of these things can be done. And we can zoom in on these 18 megabytes and look a little bit more about the internal structure of the different phases. And we see here imbalance, and we can quantify it. I've not put it here, but we could quantify by going up to the very high level again. It's something that you can navigate on this trace to very different levels. On the other part, even on the other part, you can look at a couple of iterations. Inside a couple of iterations, you can even zoom more, and you can really see there are a lot of, these are all reduces. Those all reduces, there are some of them that are long, all of this is information that really is useful for the analysis of the application for the user. But what I said is we also have in this trace, we have GPU information. So what can we see if we look at the GPU information for this one, the trace for one iteration of here is only 1.2 gigabytes. What can we see if we look at it? We can see, of course, the MPI calls because it's an MPI plus GPU application. We can see the CUDA kernels. Every color represents a different CUDA kernel. Maybe going up in the level of aggregation, and we can really see what is the total number of concurrent CUDA kernels in execution. And you see there are regions where there is a lower value, a lower number of kernels. And we have this multispectral philosophy approach where for one part of space and time, we can we display different views. In this case, I actually generated a view which is what is the time taken between exit of a GPU call and entry to the next GPU call in the CPU. What is the time between those things? And this is in the scale, 120 milliseconds for the blue thing. We see there is a structure, there are here regions with long computations, and this is essentially what justifies this inefficiency in the use of the GPUs. Too much computation in the host before launching the next set of massive kernels. I have the similar view in terms of duration of the kernels, but what I want to focus is on this view. Anything that is relevant or with kind of hints of issues that may be happening also, so different, less important in scale, in absolute scale, but can help to reduce this not being the total maximum. And one of them I want to look at is all these points which are a little bit darker, which may be executions of 30, 40 milliseconds instead of very, very, very short time between kernels. The distribution in time and space is a little bit weird, a little bit random, noisy. And that's what actually the message. There's actually possible noise in the computations because that doesn't seem to be structural of the application. Okay. And actually you can look at the duration of computation between exit of a CUDA call and entry to the next one, but you can really look at what is the time within the CUDA calls themselves. And that's what we see here. And this is another way of looking at the space and time, but with a different level of precision. And this is the duration inside the CUDA calls. And you can say, okay, there are some CUDA calls that can be relatively large if you do synchronize and you wait for many kernels to execute. But you can really focus on not every CUDA call, but only CUDA event records or only CUDA launch kernels. And we see that it does happen that sometimes there is a perturbation. So I don't want to enter into the detail of the analysis. I just want to say it is possible that navigating and zooming and focusing on features of even for same space and time region can really give you insight of things that may be happening that may have an impact in the behavior of the application. One can really look a little bit at inner level, more detail than that, and one can have views like this one, which is very similar to what you see with, with Inside Systems itself. Here we are zooming into a very small region, and we are looking at CPU and GPU, both things, So 4 CPUs and 4 GPUs out of the 32. And we are looking at the CUDA calls, and we are looking at the kernels. And well, slightly different from inside systems is that we have this link from where a CUDA kernel is launched and where it starts execution. These communication lines are used for that. But really, you can see the holes that are generated. You can really see the dependencies. You can really see, zoom in a little bit more, that sometimes it is the host, which is the bottleneck because it's not able to feed the kernels that are very fine-grained. There are other parts where the problems are slightly different. The message I would like to give here, or the experience I would like to share is, I think this world of heterogeneous computing these days has actually increased the sparsity in this space, this physical space that now has CPUs and streams, CPU threads and streams, can be very sparse. Some applications like this one only have one of each, but many applications may use multiple threads, may use multiple streams. And by the way, in what I think I've been observing is, you may use many streams or many threads, but really they don't use them at the very same time. Okay, it's a very sparsely populated space, and this is something that probably for tool developers is also something that making easy the navigation on these spaces and zooming in and out on these spaces is an interesting suggestion, I would say. I would go to the third example, which is an AI training example. So what happens on GPUs when you do AI training? What happens when you do Llama fine-tuning training on 128 GPUs? We have people at BSc, which is using this framework on top of this speed and with 0, 2, and 3, a long time. We have been doing several studies. And the kind of question is, what if I get 40, 50, 60% of peak of my GPU? Is that enough? Is that good? What's the microscopic behavior of that? So what I'm trying to use is the same study, show what happens with the same kind of tool. How do we see a run of 128 GPUs? And this is a view of the compute kernels. Every color is a different compute kernel. We also see the nickel kernels, and we see that in this case, for example, there's no real overlap. When you are doing compute, you are not doing nickel and vice versa. This is a null trace. So this is the kind of information that you can really get. Of course, here you can, as we said, you can zoom in and out. All of that is supported, but you can have additional information which has a slightly different granularity level, which is the sampling information that NVIDIA captures about what's the utilization of the NVLink. What I would like to say is that, as I was mentioning, you can aggregate. You can aggregate to the outermost, going very, very, very high away and just giving single few numbers for describing the behavior of this part of the execution, but you can aggregate just to describe, instead of the average number of GPUs being active, what is the time evolution of that property. And this is kind of very simple, very linear aggregation. For example, here I'm aggregating, you have nickel, you have the collective calls in nickel, and people enters here and leaves there. And if you were saying, okay, the time in nickel kernels are active is an indication of my communication need, I would personally say that's a mistake. When does the nickel, the collective cooperations, when do they perform most of their work? Is when everybody is inside the collective. That's the semantics of the collective, okay? So you can come out with a view that shows you when is everybody inside the collective. And you maybe, some guys, some of the 128 may be inside the collective, but some maybe not. When are all of them in the collective? You see that typically they are smaller. So the message here, I think we can really get a view, which we could say this is the 10-kilometer view, but really you can aggregate to go up in terms of a higher, farther away view, but you can also go to a deeper, more detailed kind of view. And the example I'm going to use for that is one question, one of these doubts. I mean, how important is communication in AI training? And if you look at it in this example, it's kind of, you lose 20%, okay? It may be different on different frameworks, different settings, different problems, different number of GPUs, but it's 20%, it's not 2x or it's not 3x. Actually here, load balance, which I don't know, I mean, maybe we don't typically talk that much about load balance is responsible to even a little bit more than that. Okay, but I'm going to look at the communication part, and I have the typical question. The question is to overlap or not to overlap. Should we? Should we not? What do we get? So we did a run with different parameters than the slide before, but a run where we did overlap. You tell the framework overlap communication and computation, or you tell it don't overlap it. What's the result? If we look at very, very, very high level, we knew there was everybody says communication is important. We would expect by overlapping some improvement. The result was similar time in both of them. How do we dig down into a little bit more of detail? We can obtain the trace, which happens to be each of those about 3.something gigabytes. You can actually filter them and look only at the kernels, and you can actually load both of the traces concurrently, and you can do comparisons between them in terms of synchronizing the timescales, and you really confirm that this is the case. There's a slightly different behavioral pattern, but not really a difference in execution time. So does this level of view of the traces give us much more insight about what's going on? And probably this is a situation where maybe, I mean, the suggestion is, can we describe this at a higher level, more abstract level? Can we go to the far away and see what are the efficiency metrics? And you can look at it. I mean, communication efficiency is 90%. So in this version, the previous one was 20% that you can gain. In this version, your expectations be if I overlap, should be able to gain 10%. You do overlap, what do you do? Yes, you do gain a little bit, not the 10% you expected, a little bit. Other things that you observe, by the way, I'm improving on load balance, 94 to 96. If I'm only touching overlap between communication and computation, why am I changing on load balance? What's the reason for that? And that's an interesting question. I'm not going to dig down into that because of lack of time. I'm going to focus on what I think is the most important one, which is if you look at the total time you spend in this execution, and I mean, this is one step, and this is the forward and the backward of the training. If you look at the total time you'd spend executing kernels, and you take that as a reference, and you say that for this run, you take that as 100% efficiency, you see that for the overlap case, the efficiency is 7% less. It actually means that the total time taken by the kernels here is larger than the total time taken by the kernels up here. Certainly not what we expected, or maybe not what we expected, maybe yes. Can we understand it? Which are the kernels that one would say are the more relevant in a training run, AI run? Well, we all suspect from gems, and we could try to say, go now to a little bit now lower level. What is the duration of gems here, and what is the duration of gems here? I personally prefer, rather than an aggregate number of the duration, I would prefer to go to histograms. What is the distribution of durations of gem kernels? And this is a specific one of the multiples that are being executed, one of the multiples. What is the duration of that gem kernel in a histogram? Here we have 128 histograms. Here we have another 128 histograms from 0 to 20 milliseconds in terms of duration on the gems. We see variability. There are very fast gems. There are very slow gems. There is kind of a multimodal distribution. There's a mode here, which happens in both cases, and has a kind of a spike, a mode, a dominant. The darker it means actually the larger proportion of time spent at that specific duration, which here it may be 9 milliseconds or something like that. In the other run, the spike is still, there is some spread, but the distribution is slightly different. The mode, the spike, the peak is at a lower value. So the gems here are faster than the gems here. And here we see some gems that are kind of scattered with kind of real outliers, really much larger than the standard. They don't happen here. And here also similarly, some outliers that they don't happen here. Some indication of what could we do now? We suspect on the duration of gems, we could go to these timelines and try to navigate and try to look for smaller and smaller and look here and what happens and look there at very fine grain scales. What I showed here is just looking at one of the processes, 2 back-to-back kernels. So it's one gem kernel and another gem kernel, slightly different, but which should take the same amount of time. They don't. And there are other views which are synchronized to that, which represent hardware countermetrics, like what is the tensor core activity. Darker means high tensor core utilization. Light green means not so high, for example, 31%, this value. DRAM activity, or we see NVLink activity. Or at the bottom, this one is not about hardware counters, this is about nickel kernels. And so these kind of multispectral views, I think, are very, very important to really correlate between the two things and try to come with explanations of what is happening. And easing the generation and synchronization of these views is an interesting feature. For example, is now under development or about to be released in Paraver. What is the interpretation I would like to, what would I like to focus? What is the correlations I see? Look at when is the NVLink activity taking place? Mostly when all of the processes are inside the NVLink collective call. What happens when the NVLink activity is high or is active? The NVLink is active. The gem kernel shrinks its performance. This is contention between nickel kernels and gem kernels, okay. But when one of the contending parties stops, finishes, what would you expect? You expect the other one to recover its real peak, real performance. What happens? It does not. It stays until the next kernel, and you see the next kernel, yes, does execute at full tensor core activity, but not the current one. What I'm trying to say is that if you want to dig down, you can dig down, and you end up finding behaviors that may explain variabilities, that may explain increases in amount of computation. But really digging down and zooming here, zooming there, one does not get a general perception of what is the overall impact throughout the whole execution. So you can now go up again in the scale and zoom out and derive a new analytics, new version of the window, which tells you, quantifies how much a given gem has been really stable at peak performance or not, has been perturbed and has been executing at low performance for some of its time interval. And you can see that globally. And with this, you can really see distribution. By the way, for example, there are parts of the trace where this happens in all threads. Other parts, this is a behavior observed by one thread, but not by many others. Other parts look like noise. You can try to get inside by digging now, continuing digging in and out, you can get insight from this. You could, I'm not going to go into it because I want to enter in the final point, which is, till now, we have been looking at the lowest level is essentially a hardware countermetrics. So disaggregate the execution over many instructions, thousands, hundreds, thousands instructions. I'm going to show an experience that we had in the EPI project and designing a RISC-V vector architecture where we had an infrastructure where we were able to run a binary on a software emulator, which would actually let us generate traces, and these traces would be at the level of individual instructions. So now not longer very large aggregations, but individual instructions, showing program counters, showing the type of instructions, showing vector length of that instruction, showing memory address patterns. So this is a level of analysis which is much lower than what we have seen till now, and which is very insightful, very useful in terms of providing information for co-designing, for designing the architecture. And this was done before the actual hardware was available. When the hardware was available, we did implement it on an FPGA. We have one core running at 50 megahertz. Of course, this is a poor man's emulator, okay? But you have the full real hardware running here, And of course, being able to boot Linux and you are able to do timings, but you are able to run the traces that we have seen before with Paraver. There's one thing which is new, which is you are also able to get logic analyzer information of individual signal, what happens on different buses or on different important signals. And this is the kind of cycle level information, real emulation. So this is what hardware designers use in terms of visualize with their tools, more aimed, my feeling, at verification than at real performance analysis and long-scale co-design. We translated that to Paraver, and we were able to see this behavior with Paraver, applying the powerful statistics that we have been looking at, and the zooming in and out capabilities in terms of both space and time. In this case, time, because space is only one thread, but in terms of the analytics of the functionalities that we are really applying. So here we can see what happens with running a small. This is llama, of course. This is inference, and this is a small llama, very small llama, a toy. But you run one step and you really see what is the attention, what is the MLPs, and you receive the hardware counter for those regions, be it just a single hardware counter metric for the full kernel, let's say, or if you use sampling, you can have finer grain, again, deeper in grain inside one of these kernels. And you can do analysis with that, but you can, what we said is an important thing in AI is gems. Can we now instrument the gems at even much finer grain than this? And can we display it? And this is what we are showing here. This is 32,000 cycles. And of course, I mean, this is what we can do on this, as what I said, this poor man simulator. And I actually advocate for vendors, hardware vendors, to make available emulators, software emulation platforms to application developers so that this information can be captured on real applications. And what we see here is, in the timeline, what is the instruction at the top of the reorder buffer. So this is a gem. We have loads and FMAs. And you see with this algorithm, you have one load, I think it was 24 FMAs, one load, 24 FMAs. You really see that there are potentially in flight several of those. The system is only running one at a time, because each of those FMAs is 256 double precision numbers. So it's a lot of computation which overlaps with the loads. And if you look at the memory, you can see cache misses. If you look at the memory or hits, very few hits, almost everything is cache miss. Almost everything is a cache miss. Is that bad? Well, a load instruction is 32 cache misses that we see in each of these vertical lines. If you zoom, it is 32 cache misses. Is that impacting the fact that gems are being graduated at their peak speed? Really not. You have other regions where you have a scalar core really generating a scalar cache misses. Is the stalling of the scalar core caused by these misses stalling the execution of the vector pipelines? Really not. Reality, one can get very, very high performance out of the very high utilization out of this RISC-V vector architecture with long vector philosophy. So the message for me, nevertheless, would be these kind of things, these kind of information, both with software emulation and with hardware emulation, are very useful. Very useful for hardware architects and for designers, and very useful for application developers in terms of trying to port and try to migrate and optimize the applications to squeeze most out of the characteristics of the application. And seamlessly integrating this into the higher level of instrumentation, where inside the execution that you trace with extrae, you can really get another trace with these logic analyzer signals. I think it's a very, very important, very useful feature. So just would like to conclude saying this is the kind of philosophies or methodologies or analysis that we are developing inside the POP project, that we are trying to apply to analysis of real applications. If you are an application developer and you are interested, I would encourage you to apply to a web page where we can really try to understand or show a little bit how our tools can be applied in your system, and maybe give you an external view of how your application behaves or why, digging down to a deep level in the whys and try to give complementary information to what you may already have. So to conclude, if I was to summarize into only one sentence, I would like to suggest keep dynamic range in mind, whether you are a developer of tools or you are an analyst or application developer. Try to think, what if I could dig down more? How can I support more digging down and out? This is something which I believe this dynamic range is something which is very, very, very important, very useful in HPC, but also in AI. So these are kind of my philosophical discussions. I hope I have shown that it's a little bit more than that, and I have shown with the examples that really one can get a lot of information. I'm open to questions now. If we don't address the issues you are interested, I'm still always open if you have questions, okay? So with this, I will finalize the presentation. Thank you very much.
Yeah, thank you, Jesus, for this insightful talk. Do we have any questions? We don't have a question in the chat. So if someone wants to just ask a question, you can also unmute and just ask your question directly.
Hi, so may I ask a question?
Sure.
I can start. Yes. Thank you very much for this talk. It's very interesting. Also, I got more detail about this, how the newer things that BSC is developing. One question first. Are these tools that you use for NVIDIA system, do we have also support for AMD? This
as of today, it's not available. I think people is looking. The same thing could be done. So it's and actually would be easy. And they are actually doing the tool in ways that would help the porting to other platforms. But as of today, is not available. It would be something we would actually be interested in if people is interested in, and we can really work on that. That would be good.
Okay, so I have one more question, and then I leave to others. So you mentioned that one of the problem is how we are estimating this communication pattern. So you talked about this locality is something that we have to. So how do we make sure that our performance is changing? Or because there is a problem of this memory transfer that you did not touch at this point, right? So are you measuring your trace only for the GPU, or let's say total overview of application? I don't know if I make nice.
I'm not sure if I understand. If your question is, do we account for or kind of try to quantify in the model that is being used in POP? Do we try to quantify the effect or the impact of CPU GPU data transfer and communication?
Exactly.
Is that the question?
Exactly.
Yes, this thing is accounted, is included in the model, and the tool itself is able to see when you have the data transfer kernels and when are the data, what is the actual bandwidth at the level of individual data transfer. All of this is really visible. Yes.
Okay. So thank you very much.
Actually, there's a small correction. So I know that there's ROCm 6 support in the current Extra E, and we're working on ROCm 7. I just post a little snippet to the chat that there is some more information. I don't know whether it provides the full detail as the CUDA support, but it looks like that at least there's some early support for ROCm and HIP.
With Stray, you're right. And in reality, what I presented here is with these NCs so obtaining inside system traces, converting them to Paraver. Of course, our traditional tool is Stray instrumentation tool is Extray, and we also generate essentially the same kind of traces with that. And Bernd, yes, you're right. They have done efforts on AMD systems, on Loomis, and as I said, I'm really totally not sure what is the status of official deployment in the facilities.
Okay.
One minute point. Can I ask again one more thing? Sorry, because we are really struggling with profiling things on the AMD GPU. As you know that, I mean, like inside compute, you don't have equivalent. It'd be nice if Paraver, because they save data some format, it'd be nice to have Paraver just to look at or visualize it somehow so we can get the like what is memory throughput we are getting, roofline model, etc., etc. Otherwise, one has to actually write your own code to extract this. It's a bit, let's say, annoying at this point. That's why I'm more interested in
Yeah,
about
so
this.
depending on the tools that you have, even if you want to leverage your tools, translating from that information to Paraver is something that is true, it should be done. Paraver is integrated and is coupled with a CARM roofline model, for example. So there are things there available. The
Mhm.
other question is what you said. I mean, what Bernd said. I mean, there are versions of Extrae that may already obtain some of that information. And personally, actually, you should have. I can address you to the tools team at VSC. Okay, they will tell you the exact detail of what is the actual status.
Okay, thank you.
Okay, then we have Miss Chris Adler. You can unmute and
Hello,
ask.
hi Bernd and Jesus. Thank you
Hello,
very
Iris.
much for this very interesting talk. It's so good to see how these tools have evolved. And I'm not sure how I ended up in these interesting series of lectures, but I was wondering if this is a EuroHPC presentation. Does it mean that the tools will be available on all EuroHPC machines, especially on Leonardo, since I see a few colleagues from Chinica in the call?
Yes, the answer is it should be there. It should be installed and should be usable. And some of the assessments that we have done are on Leonardo, right?
Yeah, so our grant agreement says we are supposed to install it on many Euro HP systems as possible. And I don't know the latest exact status, but the major tools like the Barcelona tools and the Ulic tools are available on the larger machines. We are slowly getting access to the smaller systems, but if you have a specific question, just ask me or so I can help basically about what the status is about a specific system.
Yeah, thank you very much. Because I do have accounts on Leonardo, and I think it might be interesting to try this out. I will.
Sure,
Thank you.
and I would actually recommend you if you are having using running programs on Leonardo and you want to apply to the project, I think it will be great for us, right? We're ready to do assessments and studies and cooperate with you, not only doing the assessment and you have it, here it is just on training and helping you use the different tools on the platform, right?
Yeah, that would be interesting. Yeah, but I'm wondering if the two colleagues from Barcelona, from Chineca, have tried to analyze our code, because I'm currently working for the SciSol code at LMU.
Okay,
and we had some.
I can tell you that from space, the project that I follow, we actually asked a couple of times POP services, and we were very happy with Extrai, and the information is amazing. So let's say but would be nice to have some kind of let's say a bit of independency so we can try ourselves. I don't know if it is already installed Extrai as a module, but I know that, for example, Radim was helping us. So he has installed in his own work area. I don't know how it is, but yeah, it'd be interesting to have it on Leonardo.
Should be, and yes, with through Radim or through some of the BSc people or the Ulic for the different tools that should be, and as Bernd said, I mean, there's an effort that should be available on Leonardo.
It is just that every Euro HPC site has their own procedures. There's not a standard simple way to install the tool. Some give us accounts so we can install them ourselves. Otherwise, as I said, there's different ways, and so we are slowly working through with different systems and with different ways of installing software and with different problems, yeah, because different computers have different tool chains, like different compilers, MPIs, and operating system, and some are easier to handle, some are harder, but we try our best.
Yeah, thank you very much. That's really great project.
Okay.
Thank you.
So any more questions? I don't see any more raised hands. So yeah, thank you so much, everyone, to join our webinar. It was kind of like very late in the year, but we hope it was some useful. There will be more webinars next year coming. We typically produce around 6 to 7 a year. And also check out our YouTube channel for the past webinars, all of them, all 38 or all 37 so far, but the 38 will come soon, will be available there. There's also then there a link to the slides if you want to just look at the slides in more detail. So thanks again for joining. And basically now I can only wish you like a peaceful upcoming weeks, some happy holidays, have a good start in the new year, and hope to hear you back in 2026 again. Thank you.
Thank you.
Bye. Thank
Thank you
you.
very much. Thank you very much, everybody.